All right, 10.5 is our next section. It is called polar form of a complex number. Polar form of a complex number. So let's recall what a complex number is. We talked about it in college algebra. A complex number is a number that has the form a plus bi. And in this case, a is going to be a real component, meaning a number in the real number system. And the bi will be the imaginary component. If we were sitting in class, I'd say, who remembers what an imaginary number is? And hopefully someone would say, oh, I know what an imaginary number is. Imaginary number is defined as the square root of -1. All right, so we have a combination of the two. So we didn't really graph these in college algebra, but let's go ahead and graph some now so that we can use these with our polar forms of complex numbers. So when we graph a complex number, we're going to put the imaginary component on the vertical axis. Imaginary axis is what we'll call that. And we're going to put the real component on the horizontal. So we'll say real axis. Graphing is really easy. We'll use some different colors here. Let's start with 3 plus I. So A is our real component. So positive 3 will go to the right 3 in a positive direction. The I, notice that the B in this case, the coefficient of I, the B is 1. So it's a positive 1. So we're going to go up in 1, and this will be our 3 plus I. It's a point just like it is in the rectangular coordinate system and actually in the polar coordinate system as well. All right, let's try another one. Let's go to yellow. Let's do -2 plus 2i. So our real number is -2. That means we go to the left 2. And the 2i is positive, and the imaginary component is positive 2. So we're going to go up 2, and this right here is -2 plus 2i. All right, one more. How about we do, let's get something in the third quadrant there. -1 and minus, as far down, my graph only goes down to -3. So we'll say -1 goes to the left 1, negative direction, and the imaginary component is a negative, so it means it goes down 3. Here we are, -1 minus 3i. All right, so that's graphing complex numbers. Well, we can also talk about let me get another color here. How about some pink? I got way more colors than my dry erase markers. And guess what? They're never going to run out. Love it. All right, we can also talk about the distance from 0. If I want to talk about how far 3 plus I is from 0, we're going to call that the absolute value. Absolute value of a complex number. If you remember, when we talked about absolute value, a complex number. When we talked about absolute value, I told you the definition of absolute value is distance from 0. It's the same here. It's how far apart, a straight line from 0, the origin, to our complex number. So the way we find that, first of all, let me show you how we're going to notate. We're going to say Z is going to be our complex number. Z is equal to A plus BI. It's just arbitrary. Z is just going to represent that. If we want to talk about the absolute value of Z, or how far it is from 0, we're going to say the absolute value of Z we could say is equal to the absolute value of a plus bi. The way we find that comes from the Pythagorean. You can see the triangle here. So it's going to be the square root of a squared plus b squared. So that a and that a comes from the real component, the b comes from the coefficient of our imaginary, and that will give us the distance from 0. All right, let's do an example. Let's say our z, our complex number, is 4 minus 3i. I want to know how far this is from 0, or the absolute value. So I'm going to say the absolute value of z, the absolute value of 4 minus 3i, is going to be equal to the square root of my a. My a is 4 squared. My b is technically negative, so we're going to say negative 3 squared, but we know what's going to happen when we square that negative. It's going to become a positive always. This is going to be, so this is 16 and 9 will be 25. So the square root of 25, which will give me 5. So the distance from 0, or the absolute value of z, is 5. Okay, so what does this have to do with the polar coordinates that we've been talking about? Let's look at a graph, and we said that this will be our a, our real component. This will be our b, our imaginary component. That's how we graphed it, right? So if we have some a down here, we're going to have, well, let's see, let's give our point first. That's going to be our a plus bi. All right, so we have, this will be a from here to here, and this will be b from here to here. And the distance, we know, is going to be that absolute value of z, right? This guy right here. I don't want to write that on there, and I'll show you why. But that's our triangle there we've created. When we talk about polar coordinates, we know that we need an r and a theta, right? That's what we learned in the beginning of this chapter. We know that our theta is right here, and we know that our r is that radius if we were to have a, an imaginary circle over here. Well, can you see what r is going to be the equivalent to? I said I didn't want to write it on here because I wanted to save room for writing the r. But the r is going to be the equivalent of the square root of a squared plus b squared. All right, so the way that we write our, let me switch over. The way that we write our complex number, the polar form of a complex number, remember we said it was a plus bi. Well, a is equivalent to the x, right? That's the x value. Do you remember what we called x from the beginning of this chapter? We said x is the equivalent of r cosine of theta, right? And b is going to be the equivalent of y. So we're going to say b is going to be r sine of theta. But because it's a complex number, we know that it's imaginary. We're going to give the b that imaginary I. So then from here, we're going to write this, we're going to factor out that r, will be r, the cosine of theta, plus, I'm going to put the I in front, I sine of theta. And this is the polar form of a complex number. Just a quick note, the book, and I notice WebAssign as well, is going to write this with a special format. So you notice our thetas are the same, right? They're exactly the same. So the way the book will write it is RCIS theta. I believe that is the cosine imaginary sine theta is what this stands for. But it is exactly the same as this right here. So I just want you to recognize that. I am okay with either way you notate that on a quiz or a test or something like that. But I want you to know that WebAssign is going to use this right here. So don't be confused when you see CIS. That means cosine imaginary sine. All right, so let's do an example. Let's switch over from, I'm going to go to black here, our example. So let's say we have z is equal to negative 2 plus 2i. We're going to write this in polar form. Right? In polar form. Well, another thing that we're going to need to know, coming from the beginning of this chapter, do you remember that we talked about the tan? The tan of theta. Let's look at this triangle right up here. The tan of theta is opposite over adjacent. So opposite is B and adjacent is A. So the tan of theta can be written as B over A. So that's important to note because we're going to have to find that tan of theta. Or we're going to have to find that theta, sorry. All right, so let's start by finding, it doesn't matter which one we start, but I'm going to start by finding theta. So if I know the tan of theta is B over A, B in this case is the 2, A in this case is the negative 2. Oh, sorry, I should write A is the negative 2. So if tan of theta is B over A, we're going to say it's 2 over negative 2. So please note, I did not bring the imaginary over here because B is just the coefficient of I. I is not included. If I simplify that a little bit, we're going to say the tan of theta is equivalent to negative 1. And I know from the unit circle that the tan of theta is going to be negative 1 in 2 places. Sorry, I'm pulling up my unit circle here so that we can talk about it together. Hopefully you have yours out. Give you just a minute if not. All right, hopefully you've written them on there. Remember we talked about writing them on there, how important it is. If not, you're looking for where sine and cosine are the same number but opposite signs because we want to divide. Tan is equal to sine over cosine. So sine and cosine are the same value but different signs at 3 pi over 4 and also at 7 pi over 4. So both of these values will give me negative 1. But remember when we were talking about converting before, we said quadrant really is important. So ask yourself, what quadrant is this? What quadrant is z equals negative 2 plus 2i in? So just doing a quick little calculation. If I know I'm negative 2 will go over here, positive 2 will go over here. I'm obviously in quadrant 2. So that means I'm looking for which angle will be in quadrant 2. And obviously this one is in quadrant 2. So that is the theta that I need to worry about. I don't need to worry about 7 pi over 4. That guy's in quadrant 4. So I have my theta. My theta is 3 pi over 4. The other thing I need is my r. That's probably the easier one because r is equal to the square root of a squared plus b squared. So a squared plus b squared. Please make sure that you square that negative. It will change things if you don't. So that gives me 4 plus 4 will be 8. So the square root of 8, which breaks down to 2 square roots of 2. So if I want to write this guy right here in a polar form, that complex number. I want to convert it to polar form. Remember, this is what I'm looking at up here. This guy up here. This is what I would write on the back of my unit circle. I would say z will be equal to, you know what, I really want to change that color so it stands out. What color? Green maybe? No, let's do something else. How about this one? I'm going to say z, well, oh, I'm on eraser. Z, oh my goodness. All right, we're going with black. Z is equal to r, that's 2 square roots of 2, times the cosine of 3 pi over 4 plus I sine of 3 pi over 4. I was running out of room there, you can see. But if I want to match, you know, if I want to match the WebAssign, it's probably going to have that CIS. So 2 square roots of 2, and then CIS 3 pi over 4. All right, so that is how we find, that's how we convert from a complex number to polar form.